Hello, everybody. I'm Hongzhu. I'm a professor of computer science at the Oxford Brookes University, United Kingdom. It is my privilege to give a talk at the International Conference on Machine Learning and Applications. What I'm going to present today is a methodology for scenario-based functional testing, which aims to improve the machine learning applications' performances. I will first introduce the notion of scenario-based testing and discuss the related work in this domain and identify the problems to apply the methodology. I will then propose a solution to the problems in a new methodology. Finally, I will report a case study to demonstrate the proposed approach, how it works, and what's the effectiveness. So, what is scenario-based testing? Put it simply, scenario-based testing is to split the test cases into a number of subsets, that each subset contains the test cases for the system on one possible operation condition. Each such operation condition is called a scenario. And then the performance of the system is assessed and evaluated on one scenario at a time. Why do we need scenario-based testing? It is because machine learning applications have been increasingly used in many critical application domains. For example, for security protection, for autonomous vehicles, for operation of large-scale infrastructures, like communication networks, like data centers for cloud edge computing, for power grid, and so on. And it is also more and more applied to medical domain. In such critical application domains, it is necessary to perform intensive testing that cover all possible operation conditions. Scenario-based testing has been widely used in the testing of a traditional software written in program. It has been proven to be efficient and effective. Many safety critical systems standards or software engineering standards requires scenario-based testing to cover all scenarios. For example, the ISO standard 26262. However, for testing machine learning applications, the research has been focused on the testing of autonomous vehicles, which is required by the ISO 26262. However, such application of scenario-based testing to the machine learning applications has limited to the generation of test scenarios, for example, on different traffic conditions, road layouts, etc. And it is also limited to the so-called validation and verification testing of functional safety. It is not widely used for testing other machine learning applications, and its effectiveness and efficiency is unknown. What is important for the testing is we want to use the test result to improve software quality. In the traditional software engineering, test results are used to debug. Once the bug is removed, the quality of the software is improved. However, for machine learning applications, After testing, we have to retrain the model and to see if it is improved. The errors we detected in the testing has very limited numbers, and they are not very indicative to what is the real weakness of the model. So after we train the model, even use the error-inducing data, it does not necessarily improve the model's performance. Moreover, if we try to improve the performance on one scenario, it may often cause decrease of the performance on other scenarios, which is often called the forget effect or catastrophic forget. So a very important open problem for the testing of machine learning application is how to improve machine learning models' performance after testing. Our proposed solution has three important components in there. First of all, we applied exploratory testing methodology, trying to discover the scenarios that the machine learning model is weak in performance. It is in contrast to the verification and validation testing, which are called the confirmatory testing, trying to assert the quality of the model. Second, we apply the datamorphic testing methodology, which we proposed a few years ago. In particular, we use datamorphism to generate data targeting the weak scenarios and use of metamorphisms to check models' correctness on each test case. Here, the key concept is datamorphisms, which are transformations of data, not just the input, but also the output, which are also called the labels. These kind of transformations preserves the semantics of the correctness of the data. The metamorphisms are the predicates on data that assert if a model is correct on a test case. The third component in our proposed method is to employ the so-called transfer or continuous learning techniques, which aims to improve machine learning models' performance rather than transfer from one domain to another. And we use it to prevent the so-called the forgetting phenomenon. Let's have a quick review of the related work in this domain first, before we say how it is performed in our new methodology. The related work can be divided into several different aspects. First of all, the testing processes. Testing for scenario-based testing has been used for traditional software for many years, in particular in the use case-driven OO methodology. In this methodology, the scenario is regarded as a linear sequence of interactions with the software under test. Scenarios are modeled in use case diagram and then further modeled using activity diagram or use scenario descriptions, for example, user stories and behavioral descriptions at the search tree. Test cases are derived from scenario descriptions or models directly and become testable data. In the context of testing autonomous vehicles, ISO standard 26262 requires scenarios to be used for the testing of functional safety. Scenario plays a central role in this testing process. It is based on a waterfall process model of software development, which is similar to the OO methodology. The earlier versions of the standard is based on traditional software engineering methodology. However, it has to be adapted to the new context of testing autonomous vehicles. So the current version inherited the conceptual model of its earlier versions, but it's not fully adapted to autonomous vehicles. Therefore, scenario still plays a central role in the testing of autonomous vehicles of functional safety. In this context, there are a number of research in the literature. For example, the earliest work published in year 2018 by Menzel et al. They defined the scenarios into 3 levels. Functional scenario, which are natural language description given by the domain expert. Logic scenario is more technically specified as a set of state variables and their value ranges. The concrete scenarios are the instances of logic scenarios where each state variable is assigned a specific value within the range, and they become the test cases. There's much work reported in the literature on deriving scenarios for testing autonomous vehicles. There are quite a few surveys. For example, I mentioned a recent one by Ding et al. In year 2023. In the more general context of testing general machine learning applications in year 2018 and 2019, we proposed the datamorphic testing methodology. It is a scenario-based approach to derive test systems for testing machine learning applications. I will not repeat too much of there because it is not directly related to the work today. So there are also a lot of research on testing techniques addressing the testing of machine learning applications. We can divide this type of work into 3 categories. The first is about test oracle. A test oracle is something which enables the test result to be checked. Much of the work has been developed under the title of metamorphic testing, which try to use metamorphic relations to check the test result correctness. The second approach is what we proposed, and based on our previous work on mutational metamorphic relations published in year 2015. It is called the datamorphic approach. The second category of these techniques is a test generation. Most of them using data augmentations to generate synthetic test data from real data. I will omit the details of the work in this area, but we want to emphasize that, first of all, this kind of synthetic data can be generated using AI techniques, for example, generative adversarial networks. This is pioneered in our work and many other researchers as well. The second type of work is about test adequacy and coverage. Scenario coverage for all scenarios has been required by the standard ISO 26262 for covering all functional requirements. It has been widely used in testing autonomous vehicles. But that is not enough to just cover all scenarios, because scenarios can combine with each other to be more complicated to test. So in year 2018 and year 2019, we proposed a set of criteria to cover different levels of combination of operation conditions. The readers are referred to our work in these 2 papers. The second approach to test the adequacy is the so-called structural coverage or white box testing. There are a number of adequacy criteria proposed in the literature. So from the review of related work, we can see the open problem we identified earlier is a problem which remains unsolved. The proposed methodology, here we consist of 4 stages and the literature process to go through these 4 different stages. The first stage is so-called exploration. It is conduct exploratory testing of the machine learning model to identify scenarios in which the model's performance needs improvement. Once we identify these kind of scenarios, which we call the suspected weak scenarios, then we perform further statistic testing of the machine learning model to confirm that the model's performance is indeed a weak scenario. Having confirmed the weak scenario is a problem, then we treat the model by retraining the model with additional training data that target the diagnosed scenarios. After we retraining the model, we're going to evaluate the model by conducting further statistical testing and to evaluate the effect of the treatment and also to see if there is any side effects. The process is an iteration of these 4 stages again and again until the performance of the machine learning model is satisfied. Here we have a few technical problems we must address before the methodology to be useful. First of all, how can we treat a machine learning model on a specific weak scenario without causing the side effects? For example, the performance could decrease on other scenarios. This is what we call the catastrophic forgetting phenomena. What we propose here is to apply transfer learning, that is, to use existing model as a basis for the retraining rather than training from scratch. Second, we need to target the particular weak scenario. We call it the targeted training. It is to use a set of training data that represents the scenario to be treated. We also need to present the side effects or forgetting effect. So the training data, we need to include a subset of the original data in the retraining subset to prevent this forgetting effect. This is what is called the rehearsal method in the transfer learning. The testing process is expensive because we need a lot of data to improve performance, especially the data for the weak scenarios. How to generate sufficient data for testing and training of the machine learning model? This is a big question. What we suggest is to use data augmentations to generate synthetic data for both training and testing. What is most important here for the use of data augmentation is not just the augmentation of the input, but also we need to transform the output, the label as well, according to the data augmentations. Therefore, the data augmentations need to be upgraded to data morphisms. To demonstrate how this methodology is going to work, here we report a case study, which is the testing of an autonomous racing car. The particular autonomous racing car we report is developed by our university's autonomous racing car team. for participating in the Formula SAE competition. The competition consists of static events and dynamic events. It is to design and build a fully autonomous vehicle from the ground up using a base vehicle provided by the competition organizer. We can have a custom array of sensors and to develop the software to control the vehicle. When the vehicle is taking part in a dynamic event, it will drive first event to drive through a straight line to accelerate and see who is the fastest to complete the track. The second event is a single lap of a track, and then a figure of 8 kind of a track, and then a 10-lap timed event. What we tested is the perception system of the autonomous racing car. The functionality of the perception system is to detect and identify the location and the color of the cones, which marks the lap. If the detection is incorrect, there are a number of consequences, ranging from the slower lap or hitting a cone, maybe, which is also a time penalty associated to it, and it could be cause the car goes to the wrong places because the cone being misplaced by the hitting of the car. The vehicle could veer off the course and then complete the fair to complete the event. The perception system is a deep neural network called Euro V5. It is customer trained using a data set of more than 640 images. It is developed by our racing team. So when we start off the testing, we've been given a model which has a relatively good performance. It was tested on 100 images from a setup, the pictures taking up the setup or track on the campus. The pictures contains the normal weather and the lightning conditions, but also have some images in the dark, objects in shadow, and with sunbeams, etc. The performance was fairly good, with the mean average precision to be above 90%. The question for us as a testing team is how to improve the performance. What we did was first manually inspected the errors made by the model. And we observed that many of the errors were in the situation when the picture was taken in a poor lighting and the weather conditions. This gives us the suspected weak scenarios in different weather and lighting conditions. For example, bright, which means the image is taken in a very bright lighting condition. Dark, which means the input image is in a dark lighting condition. Flare means the light shining straight to the lens and cause of flaring. Rain means the weather conditions are raining. Fog, raining, the weather conditions of fog. Water, which means the water is splashed to the camera lens. Speed is taken when the image is taken when the vehicle is moving fast. These kind of operation conditions were insufficiently represented in the training data and in the test data set as well, because this kind of weather and the lighting condition are difficult to collect raw data and expensive to label them. So to diagnose whether this kind of scenarios are really cause of the problem, we need to generate a lot of test data to statistically to confirm this kind of problem is really the weakness of the model. We developed 7 data morphisms one for each scenario, using the data augmentation library of the open source project AutoMode, which you can find on GitHub. So applying these data morphisms, we generate 7 data sets of the so-called mutant test cases, and these data morphisms are implemented as shown in the table here. The picture here shows the effect of data augmentations we used in our implementation. On the number 1 picture is the original picture taken on the campus, and then bright, dark, flare, fog, rain, speed, and the water, different effects you can see mimic the real situation using the data augmentations. The evaluation of the model on various scenarios confirmed our suspicion of the weakness of the model. And you can see on the look at the mean average precision in the right, in the red bars here, we can see in many cases, the scenarios, the performance on scenarios is much lower than the overall original test data. To improve the model, we build a new model M1 using transfer learning. The training data consists of 2 parts. One is a 10% of original training data, which is selected at random. The purpose of original training data is to prevent the forgetting effect. And a second, we applying data morphisms to 10% of the original training data selected at random as well. After we use M0 as a base model, we constructed the model M1. The M1's testing on the data set, the whole test data set, we found the overall performance of the model is improved by 1.61 points on the mean average precision. And in particular, the performance on bright scenario, which is the weakest scenario we see in the previous slides, has improved by 6.74 points. However, we also observed the performance on speed and the water scenarios are slightly decreased by 1.01 and 0.2 points. So the performance of M1 have improved. However, it is not so big improvement as we would expect it. So how to further improve the M1's performance becomes another question. We did again to investigate how the model fails. So we inspected the test cases on which the model fails, and we observed that the orange cones are not so well detected as other colored cones. And we did the statistical analysis again, and we found the scenarios for colored cones have variable performances. The statistical result shows that the detection of blue cone and the yellow cones are performing very well, but the detecting of orange cones are much less well as the other cones. So we confirmed that the scenario of orange cone is the problem. To improve that, we tried to build another model M2. M2, we built not just one M2, but a number of M2 to improve, to see which is the best one. So the best model is M1 we developed in the previous cycle. And we developed a data morphism called orange cone, which is to transform the cones in the blue cones in the pictures to orange cones. For example, these two blue cones in the picture are transformed into orange cones. It is implemented by a code written in Python. Again, we use 10% original training data, but we use variable numbers of data to apply the data morphism. With 10%, 20%, varying until 50% of the data selected at random to apply the data morphism. We also use the real data, real picture, for develop another version of the Model 2. We call the Model 2.R, which is using 145 images of real pictures taken by our teams independent of the testing team with 10% of original training data selected at random. The result is shown here in the picture here. And we see M2.3 has the best performance, which means 30% of the original data is selected at random and then apply the data morphism to generate synthetic data, plus 10% of the original data to train the model. Especially, it improves the performance of detecting orange cone from 60% to 65.84%, which is bigger than 30% of increase. And the performance on other cones, as shown here in the yellow and the blue lines here, the performance is fairly well remained as before. This gives us the model M2. So the case study we have demonstrated here, we can observe the following and conclude the case study. First of all, the proposed method can be useful to improve the performance of deep neural network models. Of course, the model M2 still have a space to improve, especially for the detection of orange codes. The machine model are inevitably imperfect, not 100% usually, and therefore there is a question, is there a limit for the performance improvement? Second observation we made here is synthetic data generated by applying data morphisms are as useful as natural data. Data morphism we use to generate both training and testing data. It can be very cost effective and efficient. Data augmentations may not be 100% preserve the semantics, but can still significantly reduce the cost. The third observation we have here is transfer learning techniques, especially the rehearsal-based method used in the case study, are useful to present the so-called catastrophic forgetting. Finally, the observation we have here is the more training data does not imply the better performance. For example, in our case study, Model 2.3 is better than Model 2.4 and 2.5, where Model 2.4 and 2.5 has more training data than the Model 2.3. For future work, the first problem that we want to address is how to improve the test efficiency by test automation. The case study reported in this work is conducted with the data morphic testing tool Morphy, which we reported in our paper in year 2020. Further development of Morphy to support the test activities can be proposed, can be improved the test automation, for example, to supply the facility for inspection of test cases, to filter test cases according to scenarios, to perform random selection of subsets of data as a building functionality. The second work we want to conduct in the near future is to take more future case studies. For example, how to further improve the perception system. And the second, to test the other components of the autonomous racing car, for example, the control component, the path planning component, etc. Of course, there are lots of theoretical study need to be conducted for the method to be widely applicable and generalizable for other systems. Particularly, we would like to study how to improve machine learning performances, for example, using transfer learning, continuous learning techniques to improve on particular scenarios. And at the same time, to prevent catastrophic forgetting. This is the key to the success of the method. Finally, I would like to acknowledge that the work reported in this presentation is based on the research paper we published recently in the conference on service-oriented systems engineering as a invited paper. The work reported here is partly funded by University's Research Excellence Award. We are grateful to the university's autonomous racing team for their engagement in the project and provide support in the case study. Thank you.